If you are a Python developer who's interested in machine learning, but not necessarily a data scientist or a mathematician, or if you just want to review the math behind deep learning or become familiar with the various libraries that are commonly used, then this video series may be right for you. Here I have a Jupyter Notebook, and in it I will provide a gentle introduction to NumPy, MatPlotLib, and some essential concepts from calculus such as limit and derivatives. I will avoid using linear algebra expressions and will instead demonstrate ideas using short Python snippets. Okay, so let's get started. Let's talk about the slope of a line. In order to understand why we need calculus, let's first consider the algebra used behind finding the slope of a line. Okay, so down to real business. Here's our first 5 lines of Python. I basically import the NumPy library, MatPlotLib. PyPlot is PLT. This will be used every time we want to generate a graph. I specify the style being used, so we'll just have like basically the horizontal and the vertical lines. And then I define 2 points. So the very first thing we do in our notebook, we run, it's already been run, but I'm running it again for you to show you the line has been plotted. That's it. That's the output. From Algebra 1 or from your own research on the internet, you should be familiar with the slope equation and the idea of rise over run. And I'm going to break that concept down for you if you're just getting familiar with it again. So take a look here on the line that I plotted. I'm going to add 2 additional points, one at 0, 0 RS and another 5, 5 RS. By the way, RS is red square, and you can continue to plot additional lines or points along the plot by just calling plot continuously on MatPlotLib. So take a look at my the drawing here. Let's start with the red dot in the center, and let's rise up 5 units. That's going to be the rise from rise over run. And to illustrate that, I went ahead and added on yet another point and used this here, tacking on an additional 2 points and using the minus G, which means line G, to draw from here up the 5 units. And again, we're just kind of getting familiar here with MatPlotLib and what it's like to graph a line, drop some points in the line, and I'll also be using it to just kind of to get to the point in a moment here. So rise over run, you first find out your rise, you go up, and then you come over to determine your run. You run horizontally across from the point where you stopped your rise. Again, I've graphed that here. And now we're down to the slope formula. And this is something you'll remember from some other point in life, probably, or if you're not familiar with it, you get to learn it now. So to calculate rise over run, or the slope formula, you basically take your first point and your second point, and you take the 2 y's. Okay, so the first y from this point, for example, and you subtract the second y, the difference there, and you take the 2 x's and you subtract the difference between those, then you divide them. So it's basically y minus y, the second y minus the first y divided by the first x and the second x. And basically that's it. That's the whole thing. It's easy. It's like that's the equation. It's very simple, actually. So I can call this function slope that I just defined, and I can pass it any 2 points along this line. And I went with this point 0, 0, and this point here, 5, 5. And the answer, of course, is you run the function, and the output, because we're in like a Jupyter Notebook, it just pops out here to the bottom as soon as you write. I mean, I could change this. This is, if I had a different, it's dynamic, right? But actually, what's correct here would be to use the 2 points I defined up above, and 1 is the answer. So the slope of this line is 1. And we're not going to really get into it in this particular video. But if you want to understand slope to degrees, like you say, what does that mean, 1? I don't get it. Well, go look at this table. Follow the link or Google slope to degrees, and you can get into that elsewhere. I'm not going to get into it here. But what I do want you to understand from this video is that along this line, I could have picked any 2 points. I could have got here 0.75 to point negative 25. I'm sorry, this point negative 75 to point negative 25, 25. And I would come up with the same answer. It still would have been a 45-degree angle, right? Because it's a 45-degree angle. It doesn't matter where you go along the line. And just to prove that, I just picked any other two arbitrary points and I ran it again. Of course, it's still 1. That's what you would expect. There's nothing special about this. It's easy math and it's easy to intuit. But what about if you have a curved line? And that's when calculus comes in, okay? So let me first demonstrate that by adding this little bit of code here. I didn't have to have these print lines in here. In fact, I initially removed them, but I'll go ahead and comment them out at least at first, because I just want to show you that we're basically coming up with the points to graph this curve. Now, how do we do that? I use the NumPy library. NumPy library is really useful for all kinds of working with all kinds of arrays, either generating. There's all kinds of all kinds of functions to generate series of numbers. Like, for example, this one here with time, with the a range function, it says, okay, give me from 0 to 2, give me an array in increments of 0.1. Okay, so if I just print this time out here, you'll see that. I'll just print that out right before the chart. So basically what's happening here is we're executing this little block of code. I'm grabbing the time array, which is just an array of numbers. It's the x's, basically. And I say, let's print it out here, which is what the output is here. And then I grab the amplitude. I'm not doing anything with it yet there, but I am plotting it then below at this line. So basically the output is the first array, 0 to 2, in increments of 0.1, right? So it's 0, 0.1, 0.2. And then I'm passing that into the NumPy sign function. And if I were to print those out as well, you would see that the second array, which is all of our y values, they use the sign function to calculate them, and that's what you would expect, right? So we end up with 2 arrays, a series of x's and a series of y's. We pass them to plot. I also tack on a couple of little red squares again, because I'm going to talk about that. And that's the output of the Python code. Now, when we look at this line, what do we see? Well, we say it's not a line, it's not a straight line, it's a curve. And that's different, right? We can't use the slope formula on a curve. The slope formula is based on straight lines. Now, we might be able to like run a line through our curve and get a close approximation. And in fact, that's what I'm going to do here. I'm going to create what's called a secant line. And we're going to run it through this point to up to this point. And I'm just going to go ahead and run that little piece of code so we can see what that looks like, right? So if we can say, well, I don't really know how to come up with the slope. Actually, we can see that the slope would be different. The slope of this green line is straight. It's a 45-degree angle. And this is kind of close, but it's not very close. It's an approximation, but it's not very close to this line. And so what can we do about that? Well, one thing we could try would be to move the points, the 2 points along our x-axis closer to one another. Okay, and I'll do that below. Okay, contrast this, the first line, the first secant line, to the second one along the curve. Now here, just it's visually obvious that this line is much more aligned with the curve. So we can say, oh, well, along this curve, it looks like it's probably kind of 45-degree angles, like right here where it's really tight. It would be an approximation if we took the slope of the line, of the secant line that went through the curve right here. We go, yeah, that'd be kind of close, but close doesn't really cut it, right? It doesn't in every situation. If you're building skyscrapers or a bridge, you don't want to just come up with approximations. That would lead to faulty situations. Sometimes in math or sometimes in programming, an approximation is good enough, and we can do better. We can come up with a better approximation, and that's why we're introducing calculus here. But for now, just take this away from it. If I move the line closer and closer to, and these 2 points closer to each other, I'm able to get a secant line that's very close to the curved line. And you can imagine if I got these 2 points very, very, very close, it actually might be 100% accurate. It actually would become, instead of a secant line, it would become a tangent line. It would actually touch the point along the curve, or at least virtually touch the point along the curve. Okay, let's now jump into talking about limits. And this relates to getting our two little points together closely. And it's also a concept that you see discussed quite a bit if you're reading up on calculus. And so what do we mean? Well, let's see what it means to us as a programmer. Consider this function f of x. And by the way, as a programmer, I never talk about a function of the way that I just spoke, f of x. That's a calculus terminology. That's what you, when you're studying the algebraic equations, that's how they would describe that. F of x, meaning we have a function f, and we're going to pass a series of x's into it, and we're going to get, or any given x, and we're going to get some kind of result. In this particular function f, I would just call it function f, you can see that we're going to pass in an x. We're going to do x minus 1 divided by x minus 1. And this x could be any number, say it's 5. Let's say it's 5. Okay, so 5 here would be 5 minus 1, which is 4, divided by 5 minus 1, which is 4, which is 1, right? So in fact, as you can imagine, if you passed in 7, it would give you 1. Or if you passed in 43, it's going to be 43 minus 1. 43 minus 1 should be 42. 42 over 42 is 1. Okay, it's just 1. That's the result, except for there's an exceptional case. Okay, so to demonstrate that, let's create a range, and again, just using some Python functions here, create a range. I'm going to reverse the range, call it our range, and then I'm going to loop over it with a simple for loop and print out the results saying, hey, for the f of x for wherever we are in the range, which is going to be I, the result of calling f is, and it's going to show the result. Okay, so, and here's the results below. F of x for 4 is 1, f for 3 is 1, for 2 is 1, as we expect. And then all of a sudden we hit this 0 division error. Divide by 0 errors. Hey, we're coders. Those of us who are coders, we run into this all the time. We have to protect against this. Division by 0 is a bad thing. We don't want that. Okay? But it's okay. That's what happened. If we just left this to be a completely unprotected function, we would run into this problem. Okay? Now, you can see that what happens in calculus, this condition that there are kind of limits to what we can pass in to the function, it has a name, and the surprise, English comes in pretty handy here. It's limit. Okay, so a limit in calculus is a way to express that a function must not include a certain number for an undefined case. You could think of limit this way. This is the way I'm kind of thinking of it. I've got this function. It's valid for a range of inputs all the way down to a certain point. So in our case, f of x is valid for every x except for 1, which will cause the division of 0 error, like we saw intuitively. It makes sense. We can't have that. In calculus, the limit would be described in a different way, in a more mathy way. And so I put it in quotes here. The limit as x approaches 1 of f of x is 1. And visually, it would look like what we see here in the black box. Now, that's very wordy, and a lot of times for the if you're not dropped right in the middle of a calculus class, that kind of wording is either heady or confusing or just unfamiliar. So we're not going to mess with it too much. But I did want to tie back the concept of limit to calculus because it's touching on what we're doing here, and it's also going to help us explain when we get into derivatives the little gap. Okay, the little gap that's important that I mentioned here, that is, we get closer and closer here, our slope is at more and more accurate, because as we approach the limit on our function, it becomes more and more accurate. Okay, so one thing to take away from this, as a developer, when we're writing or reviewing code and we see a real world function like the f of x in our example, we would expect conditions that protect against the division by 0 errors. I said that before, and these error handling styles, they might look familiar. Let's check them out. So you might see a programmer come along and say, okay, I'm going to write my function 1. It's going to take x, and I expect it. I understand that the x can't be 1. And so I'm going to say if x does not equal 1, then return the function. Otherwise, return none. I call this the often unhelpful null error handling approach. It's accurate, it's useful, but there are some problems with it, which I'll get into in a moment. There may be a slightly better way to do it. Then there's the universally unhelpful string error handling, where you say, okay, here's my function, it's X. I'm going to put like a try catch in it, and we're going to try to return it. If we actually hit upon a 0 division error, then we're going to say, oh man, hey, you've hit a divide by 0 error. I bet you weren't expecting a crazy string right about now. It drives me crazy when programmers do this. Don't do this. I know that you're probably debugging it. You're just giving yourself a message, but you can't leave your code like this. This is a problem. Okay. Another third approach is what I'm calling the fudge it a little tiny offset to avoid 0 case. Okay. So here in my func3, I'm taking an X, and because I know I want to avoid the divide by 0, I'm just adding a little tiny number to X. Okay, so X, I say, X, if you pass me the X, I'm always going to add just this little tiny offset. Dot 00001 to the number, and then we're going to run it. And once you round everything off, it's going to approximately give you the right result. It may be what we're after, but it's another approach, right? So you don't have to actually have try catch or an if condition in here to try to account for it. You just fudge it a little bit. Now let's compare these three approaches and see what kind of problems we might run into once we start working with our data in pandas, or we're trying to work with a set of data for some machine learning algorithm. Okay, so we're going to call the first function. We're going to take another reversed range, pass it off to function 1, and this is the array we get back. We expected to always get 1s, except for the case where 1 was passed in. In that case, we're going to return none. So it ends up looking like that. That's kind of true. This is undefined. I mean, mathematically, this makes sense. Yeah, this is good. It's all good, but it's undefined for 1, so we're not going to be able to handle that one, pass back a none, and move on. Logically correct. Let's move on to the second one. In this case, we have the case where we're passing back some kind of string because of a goofy programming style. Well, obviously, if we're trying to do math on this array, this is going to be very useless to us to have this message. So that's generally a no-no. In the third case, where we have the little fudge it a little approach, we pass in the numbers, and guess what? We actually get back what we expect, right? We get back a legitimate everything equals 1, because we never really hit the divide by 0. Nothing's really ever undefined, even if we pass in a 1. Even if we pass in a 1, it's going to be rounded up just a very small amount to 1.0001, and we won't end up with a divide by 0. And I did mention there was a case here where this could be a problem if you actually were able to pass in floating point values and you passed in this, then it would basically break our algorithm. But we're not going to touch on that today because we're looking for just different solutions, okay? And also we're just kind of trying to understand the limit and how it might be used and why it's there, so that we can get into this conversation about derivatives, which is really what I'm trying to get to in the first place. Okay, I have to jump back here for a moment because I never really explained just a moment ago. I'm actually now editing my video and coming back in and dropping in a part that I forgot to mention. The pros and cons to these three approaches as far as how it might affect you in the real world. So let's say you're doing a machine learning algorithm, and or you're just applying some machine learning to some data that you've learned. So you're learning from this big data set, and let's say you've made it all nice and you've got a bunch of different examples. Let's say you have 1,000 examples, maybe you have 10,000 examples, and you've pulled them all into this this kind of table of data. And with each row, you have you mostly have good data, but you have a couple of these none cases just like this, right? So you have some cases where there's just a null or a none or an NA basically in the data set. You run into this a lot. NumPy, you'll see this in other libraries like pandas. There's always a function to kind of like just trim those guys out. And what data scientists will sometimes do is go, well, that's not really a valid line. I can't run my math on that line, so we're just going to eliminate them. Well, if you imagine that your sample data, let's say, like I said, you have 10,000 rows. If 10 to 15% of them have these cases where none is there, and you trim them out, well, then the quality of your data set is going down, right? Because you had 10,000 examples and now you only have 9,000 or whatever you might have. And so those might have been some really great examples that you trimmed out. And why did you trim them out? Most of the data in the row was probably good, but you had some case that crept its way in where it was undefined, and so you ended up with a none. Okay, so that's not necessarily a great solution. And that's why you'll often see a solution more like the one at the bottom, where we're doing a little fudging and offsetting. So it's like, okay, for this one little imperfect part of the array, we use a little fudge factor, and because we did that, we don't have the divide by zero error. We don't have the divide by zero error, and the little offset that we added had no consequence on the data. So now, let's say all 10,000 of our samples are good. All 10,000 rows that of our data are valid. We're not having to throw out 10 or 15% of them now because of the fact that we ended up with nones or nulls in our data set. So I just wanted to kind of jump from where we are here talking about this approach and jump ahead a little bit, and then we'll swing back. Okay, that's the aside. So let's redefine f of x as a simple squaring function, okay? And below, I'm going to go ahead and say it now because I don't like to name functions f, right? I wouldn't want to call something, hey, this is function f. Well, here's a function called m, because whenever you're writing a lot of code, you need human readable names. So I'd say I would look at this function. I'm like, well, what am I doing here? I'm squaring a number. So I'd probably call this like square, so that whenever I'm down here and I'm about to use it, I'd say, okay, let's take a range of numbers here and let's square each of the x's, you know? But because we are talking about derivatives and because we are talking about concepts from calculus class, we're going to go ahead and use some of the conventions, because if you're actually like on Khan Academy or anywhere else and you're studying calculus, they're going to talk about this function as f of x. So let's go ahead and embrace the convention a little bit so that we can kind of tie together what we're doing here in Python code with what someone might be learning in a traditional, like formal setting calculus class. Okay, so let's start by plotting a line. In this case, again, here's NumPy to give me a range of numbers. And I basically say these are the x's. I say give me a range of numbers from 1 to 11. And then I want to pass x into the function f of x, which is, of course, just going to take every number that I pass in and return it squared. And this is going to be my y's. And so if I plot x and y now, what we're going to see, and kind of ignore, actually, I'll just comment this part out for a second so we can not have to look at that yet. What happens? Well, we get the range of numbers from 0 to 10 and or 0 to 11, I guess. And as we come along, as we expect, we see it going up exponentially because we've been squaring every number. So if it's 2, then it's 2 squared. If it's 4, then the y is 4 squared. 6 is 6y, you know, et cetera, et cetera. It makes sense. It's graphing. If you ever mess with a graphing calculator, this makes total sense to you. But I also wanted to bring back the secant line because I wanted to talk a little bit, again, revisit the idea of running a secant line through a curve and evaluating it at 2 points where it crosses the line. Now, earlier we observed that we get the most accurate secant line if the gap between our two x values is very, very small, almost, but not quite 0. In fact, the gap between the two x-axes is near 0. And when that happens, the line becomes tangent. And that's what the derivative basically is. It's the slope at any given point along the curve of x at y. Got it? So we're looking anywhere along here, we can say, hey, what's the derivative? Meaning, what is the slope? What's the actual slope? And derivative formula basically tells us that. And we're going to implement that in Python in just a second. Take a look at it. Another thing I wanted to mention is you can't just draw some squiggly, crazy curve up here and just take any point out of it and use the derivative formula. Like, you can't like create this crazy thing and go, oh, well, I'm really interested here where the y is 80, so let's plug y into the formula. Well, that's not how it works. It's a derivative. Okay, so you basically have a bunch of x's. You're going to apply it to a function y, and the value of y is always going to be derived from x. It's whatever you passed in as x. So if I pass in x of 6, no matter what the function looks like, it's going to be x passed into a function, and we're going to derive y. Derivative. It's one of those crazy times where, you know, the English word actually makes sense. The language is actually doing us a favor here. I remember when I first came across the term derivative as I was reading in another book, I was like, oh yeah, I don't think I ever studied that. Let's go look into it. What the heck does it mean? Well, it just means it's just being derived. It's being derived from the function of what was passed in, right? So it's just x, and you pass it in, and you derive some kind of function of y. It's very simple. It all makes sense. But you could go through 2 hours of watching videos on calculus before it really clicks to you that it's just that simple. It's just that simple. Okay, let's bounce on down below, and let's finally look at what it means to implement a derivative in Python. So again, I have my f of x, which is just a square function. And I actually pulled this straight off of another guy's video on hacking math class. So I want to give him credit here because there's lots of other simple implementations, but this one's good. And it reminds us how close that taking a derivative is to just the old slope formula of rise over run, because it's embedded right there actually. But the difference is, this is the key difference, you're not taking a fixed y point and passing in a fixed 2 points, and you're not taking a fixed point and going, oh, I know what your y is, and so we're going to pass it into the rise, put that over the run, do the math, and then return it. No, we're going to basically be taking the derivative or deriving the y from this function f of x, right? So there's two things here to note that are different. There's that, and then there's the h, this little h here. What is this h? This is the tiny gap or the time or limit as x approaches 0. This is that thing I'm talking about. This is the thing that keeps you from hitting on a divide by 0 errors. I mean, for no other reason that, well, there's actually multiple reasons, but this is one of the great reasons about it. You just can't have a run of 0. And if h was 0, which would be right on top of the line, it seems like it would be the perfect place to try to determine the slope of a curve. It would be like, well, hey, I need to be right on 0. Well, you can't, because you can't divide by 0. That's the whole problem. So you need to be as near as possible to 0. And so here, this programmer has just come up with an arbitrarily tiny number, okay? And for the rise, he says, let's call or derive from our y from x by calling this, and let's pass it x, whatever is coming into the derivative function. But let's add this little tiny amount, this little tiny gap, add to it, and then subtract f of f and just from x, which is basically your 2 points. So it's like your one, this is your point on x, and this is the point on x. It's just so tiny and just barely removed from it, just right next to it. Do the subtraction there. So your rise is going to be very, very narrow, and you're going to divide it, put that over run, and run is going to just also be that tiny number, and you're going to come up with the slope, and that's it. Boom. Derivative is the slope at that point along the line. Okay, that's how you come up with your slope along the line. Now let's just run it through a couple of numbers. So you pass in a 0 and you get back this 0.001. Why? Because that h again, because the tiny gap, because we needed to have that there. What's the derivative for 1? It's 2. What's the derivative for 2? It's 4. What's the derivative for 3? It's 6. And again, this is the derivative of the function f of x. And in this particular case, the function is just squaring it, right? That's all it is. It's just a square. You're just squaring it. So you take a whole series of numbers, you pass them in through the function, and the derivative is kind of what you'd expect. And there's a little bit of, we're rounding a little bit because actually, because of our little h, we come up with this it's 6, but it's 6. Okay, that's the answer, is 6. Let's show how this works with an array of numbers. First, let me just create a range of numbers just using the range method that's built into Python, and the map function, which will take a function to call, and then the range, an iterator over the range to pass to it, and it's going to spit out some kind of the side effect is going to be another array, the same length, but with the derivative of each. So basically, once I'm done with that, I'm going to say let's print that as a list, and you can see here we have for the range of 100 or 0 to 100, you're going to get the derivatives back. 0. For the range 1 is 2. For 2 is 4. I mean, it just keeps on going up. 3 is 6. And that's kind of difficult to work with in a, look how long this is. It's kind of difficult to look at it in this way, which is one of the good reasons that we actually will use NumPy, because it has a nice way to render all of the numbers in a nice orderly way. So I'm going to recreate that and just say for our x vals, let's use the NumPy linspace function, okay? I want to go from 1 to 10 and give me 100 of them, okay? I run that, it outputs this array for me. So I'm going to save it in x vals because I'm going to use it in just a second. So these are our x points between 1 and 10. This is, there's just like 100 of them. It's like divided out so evenly between them all. And we have a nice nice little generator here that generated 100 numbers for us. Now let's pass all 100 of those off to f of x, our function f, which is just going to square them all. Okay, we're just going to get that back and call it the f vals. Okay, and then we're also going to then turn around and we're going to take that list of x, all of our x vals, and we're going to pass them all to the derivative function. So use it again, passing the map just says map all of these to this function and give me the result. So that we'll call those the d-vals. And then we're going to plot those. So we're going to plot two lines. The x values are the same in both cases. So we say plot the x values for the x, and then a list of the f vals for the y. And again, this is it's just the numbers we're passing in squared. That's what that's going to be. And then here we're going to say give us the derivative of the function x of x, f of x, and which is of course the squared. And but this time, instead of just getting like a squared number, we're actually getting the slope. We're actually getting the slope of the line. We're getting a slope. We're actually able to have something actionable here, which is like, hey, these are the degrees along our line. And then we're going to plot them. Okay, so we've done that here below. And we can see the orange line. This is just the f of x. You take your 100 numbers and you plot them all out. And you can see that they increase exponentially. And that's fine. And then we can see that if we actually are pulling the derivatives of the function, then we produce this line, which not only is much greater, you can almost think of like, I had this series of numbers and I want to make them all louder. I want to increase them. Well, you could use the derivative for that. You just say, just do this. Like, I'm not even really concerned about slope, but I just want to see, I want to turn up the volume on all of this series of numbers. And I think this is in some ways how it's used at times in some of the machine learning algorithms. It's not so much that we're caring about the slope, but we're using it as a convenient way to kind of amplify a group of numbers that needs a little more volume. But we'll get into that later on. But for now, let's just check it out. This is our derivative line, and which tells us what the slope is. So the slope all throughout here of whatever the number might be. Let's say the number is 4. The slope is, I don't actually know what that is, but it's some number in here, maybe 17, something of that nature. Let's look at one more example. This is another interesting example that I found off of another dude's page. For his case, his function f of x just returns a sign, right? It uses in his case, instead of using NumPy, he's using the math function. I mean, there's multiple libraries of Python for generating a sine wave, and this was his approach. So I said, fine, let's just do that. And then we're just going to basically do the same thing again, get the f vals, get the d vals, and plot them again. So there's nothing has changed from what we did above, except now we're taking the derivative of a different function, okay? Instead of just instead of a bunch of squared numbers, now we're getting a sine wave, basically. So we take that and we get the derivatives and we plot them. Well, the interesting thing about the derivative of a sine is a cosine. And that's something else that you'll pick up from a math formula, but you'll just see it here visually. Once again, we can see that this line here, I think it's this line here, it could be the other line since I didn't label it. This is our sine wave. And then each one of these numbers that are passed in go through our derivative and derives another number, right? So here it is. These are the derivative numbers. And actually, it'll cross across each other. So that's pretty much what we're going to touch on this video. If you're interested in this topic or any of these topics and you want to see it go a little further, just stay tuned. I plan to come up with a whole series of these. I've got 4 different books on machine learning and I'm working through them all. And as I go through, I hit on a couple of rabbit holes. And whenever I get into a rabbit hole, like I did with this one, with derivatives, I might go off and build up a notebook like this. And then I thought, well, hey, if I'm going to do it, I might as well share it with you and give you the opportunity to tell me, no, Devin, that's not right. Or actually, that's great. Never really thought about it that way before. Thanks for explaining it. So whether I've been beneficial or not, it's out here for you to watch. And let me know if you have any comments. Just add them down in the comments below. Thanks a lot. See you the next time.